So in this lesson, we're going to look at the radiation output of a nuclear weapon. Now, we're not going to be talking about X-rays because we've already discussed those, but instead we're going to focus on something called prompt radiation. Now, the prompt radiation comes directly from the fission reaction itself. If you recall way back to the beginning of the course, there are kind of three major components to the energy created by a fission event. We have the majority of it going into the heavy charged particles or fission fragments, and then smaller fractions being distributed amongst the neutrons produced and something called the prompt gamma rays. Now, prompt radiation consists of the neutrons produced in the fission via the fission reaction, but the ones that get out, so the ones that leak out of the system, and then these prompt gamma rays. So if we look here, these two diagrams, you've seen them before. One just shows a fission event, one shows a fusion event. Now, in the fission event, we get these prompt gammas and we get neutrons coming out, and these are the ones that we're mostly concerned with. If you're talking about fusion, say in a boosted fission weapon or a thermonuclear weapon, the fusion interaction does not produce any prompt gamma rays. It merely results in prompt neutrons. Now, the energies that we're looking at for the prompt neutrons for a fission event, that's averaging, 1 to 2 MeV. But if we look at the fusion events, if we have a DD fusion or deuterium-deuterium fusion, we get about 2.5 MeV. But if we look at a deuterium-tritium fusion, we end up with a incredibly high energy neutron at around 14.1 MeV. So you're probably asking yourself, okay, great, I sort of remember this. So why do those energies matter? Well, when we look at how their energy is being deposited in either materials or biological systems, that'll come back into play. So the gamma rays that come from the fission events, the prompt gammas, they're not actually part of the fission event itself. What it is the de-excitation of the fission fragments on a very, very short time scale. So short, in fact, it looks for all intents and purposes that they came from the fission event. But, just to be clear, they don't. They come from those fission fragments, which are created in an excited state as part of the fission reaction, losing energy by immediately emitting gamma rays. So, the common parlance is to say, prompt gammas come from the fission event. Technically, they don't. So I just wanted you guys to be aware of that. Now, here's something else interesting. When you're talking about a weapon and you have all of those fission events occurring in that very short period of time while we get that energy buildup, those MeV level gamma rays, not many of them actually escape. What they're going to do is they're going to interact with a lot of that high Z material that's still left inside the weapon casing. So that, if you have, say, on average, you have about 1% of the energy of the fission reaction being taken away by these gammas, only about 0.1% of those ever actually make it away from the point of detonation. Because again, they're very readily absorbed by the case material, any high Z materials or metals that are in the case, gold, silver for the electronics, the core of the weapon itself, the plutonium, uranium, all of these things are very good at slowing down and capturing these high energy prompt gammas so that most of them never really make it out. That said, it's surprising how much damage that even small fraction of gammas can do to, again, to materials and biological systems. Okay. So this table we saw all the way in the beginning. I just alluded to it. This shows us the fractional energy breakdown of what components of a fission reaction are carrying what kinds of energies. But over on the left-hand side, we have that cool-looking sphere, and I talked about this as well. So we have some sort of point source. Imagine it's our nuclear weapon, right? And then as time moves on and the things that are emitted from the weapon expand outward, they undergo something called spherical divergence. And we can look at a cross-sectional area of the surface of that sphere, and we get an area. So that we can define how many radioactive particles are crossing that area per unit time. and this is called the flux. Or the fluence, it depends if you've been trained as an engineer or as a physicist. But because I'm a nuclear engineer, we're going to call it a flux. And the flux is usually given in number of particles per unit area per unit time. Now, two of the most common units that we work with is centimeters squared for the area, and we work in just normal seconds. So if we know how much radiation is being produced at that point source, if you will, and given some distance away from it, we can tell you with pretty good reasonable accuracy how many of those particles are going to be crossing some area in some unit time that far away. That's all this is showing. Now the radiation, the gammas or neutrons, we can do it in a number of particles, or we can do it by something called energy flux, which is we simply multiply the energy being carried by those particles by times the number of particles, and we can come up with something like joules per centimeter squared per second. There should be a little squared thing here. I don't know why there isn't. Okay, so the one I want to show is the energy carried away by the prompt gamma rays. And, you know, if we're looking at 160 MeV by the fission fragments and only 7%, you know, we're not even at 1% at the moment. So we're sub 1%, and then drop another order of magnitude for those that actually escape. So, you know, it doesn't appear that we're getting a whole lot of energy being carried away from our weapon by these prompt gamma rays. Now, again, if you remember back to the interactions lecture when we talked about photon and neutron interactions, one of the things that we talked about was something called a mass attenuation coefficient. Now, this is a measure of how a gamma photon or even a neutron kind of is going to interact with a given material. And it's based on the energy of the radiation, but also it's based on the material itself. So when we have a particle, a gamma ray in this instance, traversing through a material, it is going to undergo some number of interactions within that material. Every time it undergoes an interaction, it's transferring some of its energy into the material for a gamma ray in the form of recoiled electrons that it smacked out of off of some atoms, and now they're kind of wandering around freely, depositing their energy and ionizing additional atoms that they come across. So the particle path through the material until it gets absorbed or until it leaves, that entire path is in the volume that occurs in is the energy deposition in that volume. Hopefully that makes sense. Now, how far is it going to go into a material before it interacts? Well, there's something called a mean free path. Now, a mean free path is based off of that attenuation coefficient, but it's not based off the mass attenuation coefficient. It's based off of the linear attenuation coefficient. So what we have to do is we take the mass attenuation coefficient and we simply multiply it by the density of the material. Okay, then we get something called the linear attenuation coefficient. And the mean free path is, on average, how far a particle will go into a material before it interacts once. Okay, so mean being average, free path, how far does it go before it interacts? That's all a mean free path actually is. But if we look at the total length that a particle traverses a given material volume, we can take every mean free path, because you can calculate one mean free path, but then when that particle interacts, it changes energy. So now you have to calculate a new mean free path. And as you may imagine, as the particle loses energy, that mean free path gets shorter and shorter and shorter and shorter. But if you string them all together, you have the entire track length of your radiation through a volume where all of the energy was deposited. Now, when I say all of the energy, if a particle enters with a certain amount of energy and never gets out of the volume, then you can say all of its energy was deposited. If, however, the particle goes in, interacts a few times, and then leaves, then you have to say, well, only a fraction, some fraction of that particle's energy was deposited within that volume. Now, why is this important? When we talk about effects on materials and biological systems, they're based upon how much energy was deposited in a certain volume, either in like a person or silicon diode or an integrated circuit chip, something like that. So this works for gammas and neutrons, and it's a way to kind of estimate, how much is going to interact within a certain distance, or if you have a certain flux coming in to your volume, you can estimate how many of those are going to interact at least once in the volume. But it's not going to really tell you how much energy is being deposited, because then you have to do basically a much more advanced calculation. You have to do something like, for neutrons, something called discrete ordnance transport, or you can use something like a Monte Carlo method, which kind of rolls the dice and sees what happened each time an interaction occurs. And the way that it works out is, on average, you find out this information. So mean free path is just a measure of how far into a material can you expect a certain particle to get. Now, it doesn't sound like it's all that useful, but we're going to see that it becomes very useful when we start looking at shielding for different types of radiation and how effective it can be. Quite similar to what we saw, again, in the photon interaction, where we looked at how much attenuation occurs in a given thickness of a material for a given incident radiation. So, energy being deposited in a volume. When this occurs, the amount of energy is characterized as something called dose. More specifically, it's called absorbed dose. So absorbed dose is just energy deposited in some mass of material. Okay, that's pretty much all it is. So if we know how many particles are incident on our volume or mass of material, and we know the mass attenuation coefficient, and we know how much time has passed that these particles were incident on our volume or mass of material, we can figure out how much energy was deposited to like a first order approximation. Again, it's a little more complicated than that because the mass attenuation coefficient only gives you the number of particles that are interacting at least once. It doesn't further, spread it down the line where particles can escape. These are things that are taken into account by much more complicated models. But this is, for a first approximation, this is pretty good. Now, the units of absorbed dose is something called a Gray in SI units, or a rad in basically older, we'll call them English units. They weren't really, but the Gray is the international standard unit for right now. Now, the Grays and the rads are related by a scaling factor, so you can go from one to the other, where you can basically, a rad is 1/100th of a Gray, so a centigray is equal to 1 rad. So it's a nice convenient conversion should you need to do this. Now, when people talk especially with regards to nuclear weapon effects, when they talk about dose and they say rads, make sure to be specific about dose to what. So if you're talking about radiation on electronics, solid state electronics, you're usually talking about radiation into silicon. So your unit of dose would be rads silicon. Similarly, if you had something that was mostly comprised of carbon, you would say rads carbon, or gray carbon and gray silicon. So when you're talking about absorbed dose, you need to be specific about what absorbed the dose. Was it tissue? Was it some other solid state material? Was it a shielding material? Was it, something along those lines? Now, this is actually, some of you may have seen one of these before. This is a dosimeter. This is something that records incident radiation, and from that particular exposure that this device gets, the amount of energy that is deposited in it, they can take that and extrapolate as to how much energy or radiation interacted within a person who is wearing this badge. Again, there's a whole big conversion process that goes on, but a dosimeter's job is to figure out how much energy that is interacting within the dosimeter, and then that is used to then back calculate or estimate how much energy is being deposited in a person exposed to the same radiation field, effectively. So here we have two interesting little table figures here where we're looking at ionizing dose, which is being applied to silicon. So the one on the left-hand side assumes gamma incident gammas. So we have the amount of dose in rads, and then we have at the very bottom you can see initial observed degradation and severe degradation with probability of failure being the white and the black portions of those bars. So you can see for these different components how much absorbed dose would they have to take before they reached a probable failure limit. Now on the right-hand side, it's a little bit different. We're not looking at absorbed dose. We're looking at basically neutron flux. And it says it's a 1 MeV equivalent because that's approximately average energy of a fission neutron. Now it's in terms of flux instead of dose because translating from neutrons, from a neutron flux to a dose like we do with gammas is much more complicated. So here the reference that we're using is just the neutron flux itself. And all of that background calculation has already been done. So if we can figure out what the flux is, then we can figure out kind of how much damage we're going to impart to these different devices. Dose in tissue. Okay, this is the one we're usually concerned with. However, there are certain applications where we're concerned with radiation dose into materials for things like radiation hardening and determining if some critical system's going to fail if it's exposed to the prompt radiation from a nuclear weapon. So this is dose in tissue, and this is a pretty generic chart. And it's very specific to nuclear weapons, and it includes both gamma and neutrons, prompt gammas and prompt neutrons coming from the device. So what we see is we have our yield, our explosive yield, and our slant distance, or our true distance away from the center of the detonation. And then we can figure out how much absorbed dose in rads has been imparted to a biological target that consists of tissue. So almost every animal. It's a little bit different for plants. Okay, so that's absorbed dose. But what's this thing called equivalent dose? Well, all radiation is not created equal, right? So different radiation interacts differently with materials depending on what it is. And this is based off of something called the linear energy transfer function, or to put it more simply, how fast does a particle going into a material dump its energy? And how short or how small of a volume does this occur? So the smaller the volume that this occurs, the higher the linear energy transfer, and the higher the weighting factor for the damage that can be caused by that particular radiation. Here it's called a radiation weighting factor, and this is from the ICRP, International Council on Radiation Protection. I'm pretty sure that's what this is. And it's just a measure of how the different types of radiation compare to each other when we're talking about damage being imparted. So if we look at photons, these are our gammas, X-rays. The radiation weighting factor is 1. So if you have an absorbed dose, it translates directly to an equivalent dose. Electrons and muons, not something we really concern ourselves with, but they also correlate to a weighting factor of 1. Heavier charged particles, well, protons are very specific because they have that charge of 1. These have a radiation weighting factor of 2. Now, when you talk about heavy ions, stuff like alpha particles and even like fission fragments, the weighting factor is 20. These things deposit their energy so quickly in such a small volume that they can cause immense amounts of damage through that ionization process, because they go through the material. If you remember from the charged particle interactions, they go through a material and they're just basically smacking electrons off left and right. Those electrons then go on and further ionize other materials. And this ionization process creates a whole bunch of different effects. And that can be very damaging to both inorganic materials and also organic materials. Now, neutrons are a little bit weird. Neutrons can have a weighting factor from something like 5 all the way up to 20, and it depends on their energy. If the neutrons are pretty low energy or slow, then generally speaking, they don't impart a whole lot of energy during each successive elastic scattering. So the weighting factor for those is kind of down. So it's around between 2 and 5. This particular chart, which comes from the ICRP, shows it being at about 2.5. Now, if you go up in energy and start looking into the KeV and MeV region, we see that the quality factor starts to increase to a maximum at around 10 MeV. The quality factor is 20. So as we start increasing in energy, we start to see more energy transferred from the neutron per collision, which is in a very small space. So we're getting a lot more damage in a small volume. And it increases all the way up till we hit 10 MeV. And then it goes down, and you would probably ask, well, why does it go down? It doesn't make any sense. Well, the reason that it goes down is because the probability that a neutron will interact with anything starts decreasing with increasing energy past a certain point, and it's right around 10 MeV. So while it can transfer a lot of energy per collision, when you exceed that energy, the probability that it will do so starts decreasing to the point where, our weighting factor decreases again. So our equivalent dose is our absorbed dose times the weighting factor, and we get a new unit that goes along with it, and it's called the sievert and the rem. Now, the sievert is just the SI unit. It's named after a guy who did research into nuclear physics and radiation. And rem stands for, I didn't even know this until, I did my prep for recording this lecture. It stands for Röntgen Equivalent Man. And Röntgen was a guy who was into radiation measurement. He's got an older unit that's named after him. So Röntgen Equivalent Man is that unit applied to a volume. In this case, it was assumed it was a biological organism like a person, but it doesn't necessarily have to be. So that's what equivalent dose is. Now, I know you're having a great time, but there's one more, and that is effective dose. Now, this is specific to biological organisms. You're probably saying, why do I need to know this? Well, the weighting factor is kind of important because you need to know that the different types of radiation interact and are either more or less damaging. For effective dose, this is specific to people exposed to radiation. And the reason that I put this up here and I'm talking about it is I thought it would be a good idea for you to get an idea of, for a person, what were the most sensitive systems, biological systems in a person when exposed to radiation. So if you're talking about dose to skin, that's completely different. If you're talking about dose to like your brain or your eyeballs or your bone marrow, the different systems and components of you react differently to radiation, and some are way worse to have this energy being deposited to them than others. So ICRP, we've got I probably could have just put the last column. This is sort of an evolution of how important the different systems or how sensitive they are to radiation has evolved over time. And different systems are being added on a reasonable regular basis. So let's just look here at the one from 2007. So it used to be way back in the day that they thought the most sensitive part of your anatomy to radiation was your reproductive organs, which they called gonads. So they had them in 1977. They were rated the highest. They went down a little bit in 1990, but by 2007, they're really low compared to some of the other systems. As it turns out, the radiation to your reproductive system is not nearly as hazardous as was previously thought. More importantly, so egg or sperm, radiation damage to those, not too bad. Radiation damage to a developing organism, something like a fertilized egg that's starting to undergo cell division, up to and including something like a fetus, radiation damage there has a much greater impact. So the most sensitive systems that we know of right now is bone marrow, specifically red bone marrow, where a lot of your body's stem cells are. And your stem cells are the ones that create the new cells that replace all the cells that are constantly dying, every second in your body. So if you damage the red bone marrow, you damage those stem cells, your body can't repair itself. So that's really bad. Your colon, your lung, and your stomach all have some very specific tasks and properties in your body, that are very sensitive to radiation. Your colon has lining to it. You have digestive chemicals that are moving through it, and it's very susceptible to mutation and growth of cancers because the cells in something like your colon and your stomach are replaced very frequently. So if you damage the cells that are, basically producing these replacements in these organs because of the rapid rate of replacement, you could end up with catastrophic failure of both the stomach or the colon. The lungs are really bad and really sensitive because as radiation deposits energy in those very, very small, tiny capillaries where your oxygen and carbon dioxide exchanges are occurring, as you go in there and you start to damage the cells and damage the tissue, you remove the ability to intake oxygen and expel carbon dioxide, and then you can't breathe and you die. So also very sensitive and has a much higher weight to them than some of these other systems. And then finally, breasts, and this is, I believe, more specific to women than it is to men, although I'm not really sure. They are, so basically the tissue surrounding the breast and then the role that the breasts play, and the fact that breast cancer is one of the most common things that is experienced by women. It's one of the most common cancers. They're really sensitive. The cellular makeup of that tissue is very sensitive to radiation. And then we can go down through and see in descending order, some other parts of your GI tract, your bladder, your liver, your esophagus, your thyroid, skin not very sensitive, bone surface, it's mostly calcium, so it doesn't really do anything, so also not very sensitive. Same with your salivary glands, and surprisingly enough, your brain's not super sensitive to radiation. And then we have grouped together the so-called remainder of body, which covers all of the other different systems, which don't even, each individual system is not up to that 1% level, or that 1% level. All right, and finally, to wrap this up, before we go into talking about the biologic effects of radiation, just for an example, here are two different detonations with concentric circles, which indicate the different effects that we have associated with nuclear weapons thus far, where we have radiant exposure in calories, we have overpressure in PSI, and now we have radiation energy deposition in terms of REM or sieverts. So for 10 kilotons, we see that damage from overpressure extends, significant damage, so about 15 psi, extends a kilometer and maybe a kilometer and a half. I can use this handy dandy little scale here to guesstimate it. Your radiant exposure goes quite a bit further, so probably 2 to 2.2 to 2.25 kilometers. Now, you would expect this, but what you probably wouldn't expect is that for a small device, the the furthest of the significant effects is the radiation, the prompt radiation exposure, which goes out just a tiny bit past the radiant exposure. We'll call it a critical limit, for lack of a better term. And we'll see that 1,000 rem is a very significant dose. Now, if we look at a 1 megaton blast, what we find out is the thing that goes out the farthest is the overpressure, then the radiant exposure, and then the shortest or the least ranging effect is actually the exposure. That said, these are on the same scale. So while with a 10 kiloton blast, the significant exposure due to radiation is higher than both of the other two, and it's not when you talk about 1 megaton. The distance that those occur in a 1 megaton blast is significantly higher than it is for something like a 10 kiloton blast. All right, so that's pretty much talking about radiation exposure, looking at different types of dose and different factors that affect what dose does to either materials or biological systems. So in the next lesson, we're going to talk about the effects of radiation on people.